Bismillahirrahmanirrahim. Assalamualaikum and a very good morning. Okay, in the last lecture, before the PRU break, we have discussed on a transmission line theory, and we have discussed what happened to the characteristic impedance, the reflection coefficient, the SWR for a transmission line terminated by a matched load or ZL. So today we are going to continue with a transmission line terminated by different cases, considering the match load, short circuit and open circuit. Okay, before we continue, let's recap on what we have discussed earlier. So we have seen a transmission line with characteristic impedance Z0 and a load of ZL. So, and the line's length equal to L. So when the Z0 equal to ZL, so we know that the line is completely matched. Okay, we can assume that there's no reflection. All the signal at the input point will be transmitted to the load. All right, so there's no reflection. No reflection. So the reflection coefficient equal to 0. But for ZL, it's not equal to Z0, there will be reflection, and worst cases will be reflection coefficient equal to 1 when there's no signal being transmitted and all the signal will be reflected back. Alright, so we can calculate the reflection coefficient by considering the reflected wave divided by the incident wave, and it can be also calculated by using the impedance value ZL minus Z0 divided by ZL plus Z0. Alright, so we have also looked at the VSWR, or the voltage standing wave ratio, in which it considers the Vmax and Vmin. So standing wave basically happens within the lines due to the reflection and transmission of the signal. So it is the ratio between 1 plus the reflection coefficient divided by 1 minus the reflection coefficient. And we have also looked at the percentage of power loss and the total power transmitted from a transmission line terminated by a load ZL. Another parameter, basic parameter that we are about to look at is the input impedance. So we have seen that the ZL is basically the endpoint or the termination of the transmission line. Okay, but at the distance Z equal to minus L. So we assume Z equal to 0 is at the load point. So at a distance of minus L from the load, so the impedance looking towards the load is called Zin. Right, so this is Zin, it's looking towards the load. Right, this is the input impedance, or it is also known as transmission line impedance. Alright, so the Zin can be estimated by the following equation. So it's basically the Z0 multiplied by this equation, 1 plus the reflection coefficient and 1 minus the reflection coefficient. And when you expand the reflection coefficient, so reflection coefficient equal to ZL minus Z0 divided by ZL plus Z0. So you can get the Zin equation is further expanded into this. Okay, so what will be the Zin or the input impedance is depending on the load and also the distance. Alright, so in terms of the admittance, we can represent the equation by using Yin equal to the following equation. Okay, next we are about to look at the special cases of lossless transmission line termination, considering other conditions than the load termination. Right, so we are about to look at the open circuit and also short circuit. and also open circuit. Okay, considering the same transmission line as earlier, so now the load is, or the transmission line is terminated by a short circuit. Okay, terminated by a short circuit. So in this case, the ZL equal to 0. So the input impedance looking towards the load is known as input impedance. Alright, so in this case, when ZL equal to 0, so we know that we can get the reflection coefficient equal to -1. Okay, since ZL equal to 0 and 0 minus Z0 over Z0, so we get -1. Alright, so in terms of the Zin, the input impedance, from the simplified equation from previous slide, so for a transmission line terminated by a short circuit, the Zin can be estimated by this equation. JZ0 tangent beta L. Beta is the phase constant and L is the length of the transmission line, and we can see that the Zin is purely imaginary for any length of L. Okay, and the values taken in between positive J infinity to negative J infinity. So, and it independent on L. For example, when L equal to 0, so Zin will be 0. For L equal to lambda over 4, so if the L equal to lambda over 4 at the respective frequency, so the Zin will be equal to infinity. Okay, so when the L equal to lambda over 4, okay, that's open circuit. Okay, so the Zin will be infinity. Okay, so another case when the transmission line is terminated by an open circuit. So now again the Zin will be looking towards the load point. So in this case, the load is open circuit, so we can assume that ZL equal to infinite. Right, so the reflection coefficient when ZL equal to infinity, so infinity divided by infinity, it is equal to 1. And the standing wave ratio is infinite. So what is the SWR equation? It's 1 plus the reflection coefficient divided by 1 minus the reflection coefficient. Okay, so in terms of the Zin or the line impedance, so for a transmission line terminated by an open circuit, so the Zin is equal to this negative JZ0 cotangent beta L. So, and again it depends on the L. If the L equal to lambda over 2, so the Zin will be equal to ZL. So from here, if Zin equal to ZL, meaning that a half wavelength line, at half wavelength line, or any multiple of lambda over 2, okay, the Zin and ZL, there's no transformation. Okay, so though there's no load impedance transformation or any changes on the load regardless of the characteristic impedance, so the Zin will be equal to ZL, doesn't matter of what is its characteristic impedance at L equal to lambda over 2. But if the line is quarter wavelength long or multiple of quarter wavelength with the n equal to odd number, n equal to integer 1, 2, 3 and so on, so the input impedance is estimated by Zin equal to Z0 squared divided by ZL. Okay, from the two special cases that I've shown earlier, the short circuit and also the open circuit, so we can summarize the condition. If ZL is short circuit, so we have ZL equal to 0. Okay, so the input impedance or the line impedance equal to this equation. So it depends on the L. And if ZL is open circuit, so ZL equal to infinite. So the input impedance or the line impedance equation is equal to this. And if L equal to lambda over 2, we have seen earlier that ZL equal to Zin. So there's no changes in the load impedance, regardless of the changes in the Z0. And if L equal to lambda over 4, the Zin will be equal to Z0 squared divided by ZL. And let's look at the use cases, or in practical, a transmission line will be connected to more than one structure, right? So in this case, for example, let's look at reflection and transmission at the junction of two transmission lines, which having different characteristic impedance. Okay, so in this case, we assume that the characteristic impedance of the first line, this is the first line, and this is the second line, is not similar. Okay, so at this point we can assume that the output from the first line will be fed into the second line. Okay, but at the junction there will be also reflection. Okay, some reflection of the signals at the joint or within the first transmission line before it be successfully transmitted into the second line towards the load. Okay, so the input impedance seen by the feed line is equal to Z1 if the load line is infinitely long. So we don't know where the load is positioned, or where exactly the ZL is. So in this case, if the load line is infinitely long, or if it is terminated by its own characteristic impedance, so in this case, we know that the characteristic impedance is not equal to the ZL. So therefore, we can calculate the reflection coefficient by considering the characteristic impedance of the individual lines included in the system, right? So in this case, Z1 is the second line characteristic impedance minus the first line characteristic impedance, right? So in this case, since we don't know the position of the load, so we assume that there's no reflection from its far end. Okay, so this is the first transmission line, and then the signal goes into the second transmission line. Oops. Okay, sorry for this. So the second transmission line, and it's far end until they reach the ZL. Okay, so if the load line is infinitely long, so we can assume that the L is infinite. So we assume there's no reflection from the far end. Why? Because when there's reflection, okay, the signal may have been attenuated. So we can assume that the signal been transmitted to the load. Right? So considering this condition, so we know that not all the incident wave is reflected. Some is transmitted onto the second line. So at this point, some of it will be reflected back, and some of it will be transmitted onto the second line. So the total voltage at Z equal to is less than 0 at this point can be calculated by this equation, and depending on the reflection coefficient, the rate of reflection. And at Z larger than 0 towards this direction, so we can estimate the voltage by considering the transmission rate, right? So the T is known as transmission coefficient, in which it can be calculated by 1 plus the reflection coefficient. Right, so in this case, the reflection coefficient for a two transmission line connected together can be calculated by the second transmission line minus the first transmission line characteristic impedance, okay, divided by the sum of them. Right, and in dB, the transmission coefficient between the 2 points in a circuit is known as insertion loss, IL. So insertion loss is the measure of transmission coefficient between 2 points in a circuit. So it is negative 20 log the transmission coefficient, and it is in dB. Okay, let's look at an example. Okay, given a transmission line with length of lambda over 8 and 50 ohm characteristic impedance. So characteristic impedance is the Z0, is terminated by a 100 ohm load impedance. So this is your ZL. So a transmission line. So the L is lambda over 8 and terminated by ZL. Okay, so your Z0 equal to 50 ohms, so Z0 is here. So ZL equal to 100 ohm and Z0 equal to 50 ohm. So we know that in this case, Z0 is not equal to ZL. So that's mismatch. So some of the energy may be reflected back. So referring to this transmission line, determine the input impedance, input reflection coefficients, and VSWR. Next, the input impedance, input reflection coefficient, and VSWR if the load is changed to short and open circuit. So the first consideration, ZL equal to 100, but in the second question, you need to replace the ZL with short circuit and open circuit. And the third one, with the 100 ohm load impedance, okay, the same load impedance, determine the input impedance, input reflection coefficient, and VSWR if the length of the 50 ohm transmission line is changed to lambda over 2 and lambda over 4. So when you change the length, meaning that there's special cases to be considered. Okay, let's discuss the solution. So as the question earlier, so given the ZL equal to 100 ohm and Z0 equal to 50 ohm, and then given the length of the transmission line equal to lambda over 8. Okay, determine the input impedance, input reflection coefficient, and VSWR. So the transmission line, okay, you have the ZL. Okay, so you have the ZL. Here is you have your Z0, and you have the Zin facing towards the ZL, and the length L equal to lambda over 8. Okay, determine the input impedance, okay, based on the equation that we have looked at earlier. So Zin equal to Z0 ZL plus J Z0 tangent of beta L divided by Z0 plus GZL tangent beta L. Right, you know the Z0, you know the ZL, so you can calculate this straight away. So your Z0 equal to 50, ZL equal to 100 plus G50 tangent beta. What is beta? So beta is the phase constant. From previous lecture session, we know that lambda equal to 2 pi over beta, or lambda equal to C over F. So in this case, beta equal to 2 pi over lambda. Okay, so you can replace the beta equal to 2 pi over lambda. So 2 pi over lambda, L given is lambda over 8, divided by Z0 is 50 plus GZL 100 tangent, again beta is 2 pi over lambda and L is lambda over 8. Okay, so you can calculate this. So your Zin equal to 40 minus G30. Okay, please calculate this properly. So I recommend you to write down the general equation, include the values you have in, and your final answer. Okay, this is the first one, the input impedance. Next, the input reflection. So input reflection is input reflection. Okay, you should read the question carefully. If the question just asks you about reflection coefficient, so you know it is ZL minus Z0 divided by ZL plus Z0. But if it is input reflection coefficient, so you should consider the reflection input reflection coefficient at the input point. Okay, at this point in. Okay, so it is equal to Z input minus Z0 divided by Z input plus Z0. So in this case, Z in is from your calculated value earlier. So it is 40 minus G30 minus your Z0 is 50 divided by Z in 40 minus G30 plus 50. So you should get your input reflection coefficient equal to negative G 0.33. Okay, you haven't completed yet. Please make sure you read through the question carefully. You have 3 items to be addressed here: the input impedance, input reflection coefficient, and VSWR. And lastly, the VSWR equal to the Vmax over Vmin, or you can also calculate this by using the reflection coefficient that you have. So VSWR is basically the ratio between the magnitude of your reflection coefficient, or S11, divided by 1 minus the magnitude of your reflection coefficient. So 1 plus the magnitude of your reflection coefficient that you have divided by 1 minus the magnitude of your reflection coefficient. So in this case, it is 1 plus 0.33. Okay, so from this reflection coefficient, so get the magnitude of it. So then you perform your calculation. 1 minus 0.33. So you should get the VSWR equal to 2. Okay, next let's look at the second question. Determine the input impedance, input reflection coefficient, and VSWR if the load is now changed to short and open circuit. Right, so let's consider the condition A. So for short circuit, sorry for my handwriting, short circuit. So in this case, your ZL will be equal to 0. Here is your Z0, and here is your Zin. Alright, remember the Zin equation if you have short circuit. Right, so for short circuit, your Zin equal to JZ0 tangent beta L. So in this case, it is equal to J, your Z0 earlier equal to 50, tangent beta again 2 pi over lambda divided by your L, lambda over 8. So you should get your Zin for short circuit equal to J50. Okay, next the input reflection coefficient. So reflection coefficient input equal to, again, write down the general equation, Zin minus Z0 divided by Zin plus Z0. So your Zin is from your calculated results before. So it's J50 minus your Z0 equal to 50 divided by J50 plus 50. So you should get your reflection coefficient, input reflection coefficient equal to J1. Okay, for short circuit, another one, you need to calculate the VSWR. So VSWR equal to the ratio between 1 plus the magnitude of your input reflection coefficient plus 1 minus the magnitude of reflection coefficient. So the magnitude of J1 equal to 1. So 1 plus 1 divided by 1 minus 1. So your VSWR for short circuit will be infinity. Again, let's move on to B for open circuit. Basically, more or less the same steps, but you need to make sure that you use the open circuit equation for the input impedance. So open circuit. So in this case, your ZL will be equal to infinity. So this is your Z0, and you have your Zin here. All right. So for short circuit, we know that your Zin is simplified to negative J Z0 cotangent beta L. So this is equal to your negative J, your Z0 is 50 cotangent beta 2 pi over lambda. Your L is lambda over 8. So you should get your Zin for open circuit equal to negative J50. Okay, please check the values again. If I have wrongly calculate, please make sure you correct it. Right, next is the input reflection coefficient. So the same steps using Zin for open circuit. So this one int equal to, so I want you to practice a lot. Make sure you write down the general equation first before you calculate the values. Zin minus Z0 divided by Zin plus Z0. So which is equal to, so your Zin just now is negative J50 minus your Z0 is 50 divided by negative J50 plus 50. So you should get your input reflection coefficient equal to negative J1. Okay, lastly, the VSWR for open circuit. So VSWR, same steps, 1 plus the magnitude of your reflection coefficient divided 1 minus the magnitude of reflection coefficient. So here magnitude of negative J1, 1 plus 1 divided by 1 minus 1. So you should get the VSWR equal to infinity. Okay. Let's move on to the last question, question 3. With the load 100 ohm load impedance, determine the input impedance, input reflection coefficient, and VSWR if the length of the 50 ohm transmission line is changed to, okay, you have different length now. So you have this one, and you have ZL fixed to 100 ohm, and you have your Z0 equal to 50 ohm. But now the L is changed to lambda over 2 and lambda over 4. Sorry, L. So you need to consider both L in your calculation. So here is L, and then you have again your Zin facing towards the ZL. Right, so when you have the L, the variation of L, remember we have the special cases in which if L equal to lambda over 2, so your Zin will be equal to ZL. Oh, will be equal to ZL. Okay, another condition, if L equal to lambda or 4, so your Zin will be equal to Z0 squared divided by ZL. Right, considering the first case, case 1, if L equal to lambda over 2. So in this case, we know that for special case, your Zin will be equal to ZL. So in this case, it is equal to 100 ohm. Okay, so the load determine the input impedance. Okay, so the input impedance automatically equal to 100 ohm since L equal to lambda over 2, so Zin equal to ZL equal to 100 ohm. Next, the input reflection coefficients. So input reflection coefficient. Input. Okay, so again Zin minus Z0 divided by Zin plus Z0. So your Zin equal to ZL equal to 100 minus your Z0 is 50 divided by 100 plus 50. So it is equal to 0.33. So the third one is the VSWR. So again, 1 plus magnitude of reflection coefficient, 1 plus 0.33 divided by 1 minus 0.33. It is equal to 2. Okay, same goes to the second condition when lambda is equal to 4, but you need to make sure that you know the condition. What happened to Zin when L equal to lambda over 4? Okay, so as discussed earlier, when L equal to lambda over 4, so the Zin will be equal to the following equation. So the second condition, when L equal to lambda over 4. So you know that your Z in will be equal to Z naught squared divided by ZL. So Z naught squared is 50 squared divided by ZL is 100. So it is equal to 25 ohm. Okay, so it's equal to 25. Okay, next is the reflection coefficient. Okay, Z in minus Z naught divided by Z in plus Z naught. Okay, look at how many times I wrote down the general equation. So same goes to you. When you answer your quizzes or tests or final exam, make sure you write down the general equation. Then you include the values in before your final answer, or else you'll miss lots of marks for the steps. So this one equal to your Z in here is 25 minus 50 divided by 25 plus 50 equal to negative 0.33. Okay, finally VSWR equal to 1 plus divided by 1 minus equal to 1 minus 0.33 divided by 1 plus 0.33. It is equal to 2. Okay, finally, before we end the topic, so please spend a few minutes to fill up the table by calculating each parameters in the empty columns or row. Then you need to discuss the relation. Okay, what happened when you have a positive or negative reflection coefficient, and what will be your magnitude or total loss, and what will be your return loss, what will be your VSWR, whether it is within the preferred limit, how about the total power loss, and the percentage of transmitted power.